Hi, we're going to solve problem 4C from the homework now. This problem consists of a simply supported beam with an overhanging end and a distributed line load, here colored in orange, between supports A and B. The live load, or the line load, is equal to 4 kips per foot. And we have been asked to solve for the shear diagram, the moment diagram, and the deflected shape. So step 1 in these problems is always to find the reaction forces first. So let's go ahead and sketch in the reaction at A and the reaction at B. We write our equations of equilibrium. The sum of forces equals 0. So we have 4 kips per foot times 11 feet. That force is going down. And that's equal to R sub A going up plus R sub B also going up. Multiply this out, the feet cancel, so we have 44 kips down equals R sub A plus R sub B. Now the second equation we need to solve the problem is the sum of moments equals 0. So first let's consider where we want to sum moments about. It's usually convenient to pick one end of the beam. So let's pick point A. Sum of moments about point A equals 0. So if you look at the distributed load, we have 4 kips per foot times 11 feet equals 44 kips. And the resultant of that is going to be right here in the middle of the beam. In other words, half of 11 feet. So I'm going to take those 44 kips and multiply them by half of 11, 5.5 feet. And that force is going to cause a clockwise moment. And we're going to set that equal to R sub B, and its distance from point A, or the yellow dot, is 11 feet. Let's put this in our calculator. 44 times 5.5 divided by 11 equals 22. So R sub B equals 22 kips. Feet cancel. And now to solve for the reaction at A, we have to plug it back into this equation. So we have 44 kips equals R sub A plus 22 kips. Subtract out 22 from both sides, yielding R sub A equals 22 as well. Now it's time to draw the shear diagram. We start from the left end of the beam. The first force we encounter is the reaction of A, 22 kips up, so we go up 22 kips. Now between point A and point B, we have this distributed load. 4 kips per foot times 11 feet is 44 kips. 22 minus 44 is negative 22. And we know that anytime we have a distributed load, the shear diagram is going to be sloped and linear. We come down to this point, and we only have one vector left on the beam. R sub B equals 22 kips going up. So we come up the 22 kips, and we close off our shear diagram at 0. We look at the remaining 4 feet of the beam, and there's nothing happening here. So this is our shear diagram with a maximum shear of 22 kips at both ends. Now, to do the moment diagram, I need to take the areas of the shear diagram. So I'm going to call this area 1 and call this area 2. Since this is 22 kips and this is 22 kips, you can look at similar triangles, but we know that this point has to be halfway between points A and B. In other words, 5.5 feet here and 5.5 feet here. So let's take the area of number 1. The formula for area of a triangle is base times height divided by 2. So we have a 5.5 foot base times a 22 kip height divided by 2. 5.5 times 22 divided by 2 equals 60.5, and look at the units, kip feet. Area number 2, it's also 5.5 base, 22 kip height divided by 2. It's the same area, 60.5 kip feet. So to do our moment diagram, we know the moment at this first pin connection has got to be 0. And we recognize that when the shear diagram crosses 0 here, we'll have a local maxima or minima of the moment diagram. So let's consider between point A and this midpoint. This area of the shear diagram is positive because it's above the 0 line right here. So therefore, we have to go up in moment 60.5. Same thing on this end, it's negative, so we have to go back down 60.5. Over here on the end, we don't have any shear, so also we don't have any moment. That all stays blank. Now we recall that when we have a sloping line for shear, our moment has got to be curved. So the only question left is whether the moment is curved concave up or concave down, or smiley and frowny. The way that's determined is we see that the shear is a downward sloping line, and therefore the moment is concave down. So this is what your moment diagram looks like. Final step is to sketch the deflected shape, and we know that we have a support here and a support here, so we have no deflection at those points. The load is in the middle, so we have a simply supported curve, and then the end of the beam, to maintain continuity, comes up straight like this. And that's the end of problem 4C.